So our first panel this morning deals with a scenario that I think all of us as pilots will never have, we hope we never have to face, is a fire on the aircraft, and one that may not be easy to deal with. So I'd like to turn the stage over to our colleague, Mark Rogers, who is not only director of ALPA's Dangerous Goods Program, but as you've heard, is an internationally recognized industry leader in the field of safe transport of lithium batteries. Mark, over to you.
Thank you, Chuck, and good morning, everyone. As he just mentioned, I've been involved in dangerous goods now for about 15 years, but we have decades of experience before that in the dangerous goods world of safely transporting commodities that could be hazardous to an aircraft. However, unlike most dangerous goods, say a flammable liquid, where the dangerous goods regulations are predicated on making sure that that package is safe, lithium batteries are a little bit different. For a flammable liquid, the biggest concern you have is that the package will fail and you'll have a spill, but you still need an ignition source to have a problem. And once that package is safe, the transportation system has ensured that further packages can be safe on the aircraft. Lithium batteries are a little bit unique. All you need for a lithium battery problem is improper packaging to get a short circuit, maybe damage to the package, or perhaps a manufacturing defect that hasn't been detected over months and months of transport. Additionally, lithium batteries are something that are a little bit different than, say, sulfuric acid or acetone, in that they'll be shipped many times over their life. They're not just shipped once and used. And if you do have a problem with lithium batteries, you can have a fire hours after the damage has occurred, months after the manufacturing defect has occurred. Or if you have an external fire from any other source, you can easily involve the lithium batteries. One of the other unique aspects of lithium battery transport are the quantities that we're talking about. You never have an airplane filled with flammable liquids, but we have cases today where an airplane will leave an airport in China for Hong Kong filled with almost entirely lithium batteries. Last year, there were over 6 billion cells produced, and that's several billion more than a few years ago, and projections are that those will continue to increase. The dangerous goods regulations focus on the package, and that's the biggest reason why they're not the answer to this problem. It doesn't matter if we put a new label on the package. That won't stop the fire. Having it on the pilot notification form is very important, but it won't stop the propagation of a fire. What we need are technological solutions to this problem. We need a way that looks beyond the dangerous goods regulations and looks at the overall safety of the aircraft. Because even if a single package is safe, once you put hundreds of thousands of those on an airplane, you have a totally different risk profile. And so today we've put together a panel that will look at going beyond the dangerous goods regulations. For as much as I've focused on that, and as important as having these properly regulated with the proper labels and notification and training and everything else that goes along with that, to actually solve the issue, we need to look beyond those regulations and find ways to mitigate the problem on multiple levels. We have 4 panelists today, starting with Harry Webster from the FAA Technical Center in Atlantic City. And Harry is going to outline just what the problem is and what you would expect to see should a fire occur on the main deck of an airliner involving lithium batteries. From there, we'll move to the technological solutions with Mr. John Green from AkroFire, who's developed a unique packaging solution that could potentially stop a fire at the package level before it propagates among the aircraft. Then we have Bob Brown from the Independent Pilots Association and UPS Safety Task Force, and he will highlight the important work that UPS has been doing in this area in terms of fire containment covers and container-based suppression systems, among other safety improvements. And finally, we'll have our own Rich Hughey from FedEx, an ALPA member, to highlight what FedEx has been doing as well, and our positions on the continued safe transport of lithium batteries. So with that introduction, I'd like to ask Mr. Harry Webster to begin his presentation and to highlight just what the problems are. Thank you.
Thanks, Mark. Could I have the presentation put up? This morning I'm going to be giving you a little update on some work we've done at the Tech Center. We've been looking at lithium batteries for about 10 years. The most recent work, we actually ran full-scale fire tests on board an actual aircraft. Before we go into that, it's probably worthwhile summarizing a little bit of what we've discovered over the years. Starting with lithium-ion cells, we found that they were capable of something called thermal runaway, which we had never run into before. This can happen through cell defects, cell damage. If you heat the cell, if you rapidly discharge or overcharge the cell, all those things can trigger thermal runaway. Thermal runaway results in a high case temperature, and lithium-ion battery can easily exceed 1100 degrees Fahrenheit. It results in the release of a flammable electrolyte. And most importantly, it generates enough heat to cause any cells that are adjacent to the cell in thermal runaway to also go into thermal runaway. This process will propagate throughout the entire shipping box and also from box to box within a shipment. Another finding with lithium-ion batteries, they can experience what the industry likes to call catastrophic disassembly. We call it exploding. Ion cells generally do not self-ignite, but the high case temperatures easily ignite current packaging materials, which in turn ignites the electrolyte, which adds heat to the system and speeds up the process of propagation of thermal runaway. 1301, the suppression agent that is in most Class C compartments, can suppress the electrolyte fire. However, in the presence of halon, or if there is no ignition sources, the unburned hydrocarbons accumulate, and you increase the risk of a flash fire or an explosion at some point. Looking at lithium metal batteries differ from ions. Ions were rechargeable. Metals are single-use throwaway cells. Biggest difference between them is lithium metal cells actually contain metallic lithium. They are again capable of thermal runaway for much of the same reasons as ion cells. Even higher case temperatures exceeding 1400 degrees Fahrenheit, and the actual fire can exceed 2200 degrees. They release a flammable electrolyte, and in addition to that, they also release molten burning lithium. And they again can generate enough heat to cause adjacent cells to go into thermal runaway, and this again will propagate throughout the box and then from box to box. Another key difference with metal cells is the fire buildup is extremely rapid. They also can explode. When they do explode, they generate a fair amount of pressure. They're self-igniting, and they will rapidly ignite the current packaging. The 1301 will suppress the electrolyte portion of the fire, but not the lithium portion, and seems to have no effect on the speed of propagation of thermal runaway. And again, if you can keep the electrolyte from burning, you end up with an accumulation of hydrocarbons, increasing the risk of flash fire or explosion. After 10 years, we reached the point where we wanted to see just how the aircraft would react to a relatively large full-scale fire. And for purposes of that, we used a 727 that was kindly donated by FedEx. And the objective of these tests basically was to document the characteristics of fires involving large numbers of small lithium batteries in a realistic aircraft environment. It's worth reviewing that an upper deck compartment on most freighters only has a fire detection system. There's no halon 1301. It does have the means to shut off ventilation, and theoretically the means to exclude hazardous quantities of smoke, flames, or noxious gases from the flight crew compartment. So we developed a test plan. We were looking at, we settled on a fire size of about 5,000 cells, keeping in mind that many shipments can exceed 50,000. So we ran, or we were looking at 5,000 cells of lithium ion. We'll run a separate test with, as it turns out, 4,800 of lithium metals. And then as a control, we used another 5,000 battery load of mixed older style batteries of alkalines, NiCads, and nickel metal hydrides. We used 2 different ignition sources, ran 2 separate tests for each fire load. One where we simulated a thermal runaway, and the other one where we had a small adjacent fire to get the cells involved. So we instrumented our 727, thermocouples everywhere, smoke meters, heat calorimeters. We measured noxious gas quantities and extensive video coverage. We actually repeated all that in 3 locations: the main deck, lower forward compartment, and also on the flight deck. And probably the most important thing in this simulation was to get the airflow within the aircraft correct. We wanted to try and simulate a plane in flight while still on the ground. Air packs are configured differently, at least on a 727, depending on the location of the fire. If the fire is in the lower deck, you set it up differently than if it's on the main deck. So with the help of the Boeing company, we developed 2 configurations for both for a Class E fire and also for a forward Class C compartment fire. I won't be talking about the Class C fires today, but that information will be available on our webpage. To verify that we had the configurations right and we were getting realistic results, we conducted air exchange tests and got very, very good numbers. In the unpressurized configuration, which is what you would have in a Class E compartment fire, we got air exchange rates of about almost 48 minutes while maintaining a 1.7-minute air change on the flight deck. We were assured by Boeing that these were good numbers. We conducted a couple different baseline tests. This one was to verify the operation of all the instrumentation. This was just a cardboard load. And then, can I have this video run, please? We also ran tests outside of the aircraft prior to running the tests in the aircraft to get a handle on how big a fire a 5,000 cell lithium battery fire would be. These tests weren't run concurrent, but we have them synced up here on the screen. Ignore the gentleman walking in front. The cells to the left of the screen are lithium metal cells. The cells on the right are lithium ions. Very different behavior, particularly in terms of the timeline. Here at 9 minutes from the time we simulated a thermal runaway, we already had a pretty good fire going on the lithium metal side. Still had not broken through the packaging on the lithium ion side. A little difference in the way the screens look. We had a cage on the metal test. We didn't use a cage on the ions because our safety people saw the ion test and said, you will cage the metal test. So the metal fire was over and done in about 16 minutes. We consumed all the cells, extremely hot. The remains of that fire stayed hot for hours and hours and hours. We had over 2,000 degrees down in the middle of that battery stack. So at this point, we're roughly 19 minutes in from the time we began the simulation of thermal runaway. We've just broken through with the ion test. One interesting thing here, if you watch the debris field around this, the ions really tended to what we call rocket. They we had some cells that shot over 130 feet from the base of the fire. One of our video people said it was like being back in combat because these flaming things were shooting over his head, and you can see why our safety people said we should cage the next one. So this test, I'll just talk ahead a little bit. Okay, it took roughly an hour to consume all the batteries versus 16 minutes for the metal cells. It's a big difference in the way the fire builds up. So looking at our Class E main deck tests, we put the aircraft in emergency mode, which consisted of a high ventilation to the flight deck, no ventilation to the main deck. And essentially on a Class E compartment, you were trying to starve the fire of oxygen. In this picture, you can see we had a ARF vehicle standing by to assist should we need it. Should mention that we had outfitted this aircraft with a deluge water system to control the fire should it have gotten out of control. We were monitoring temperatures not only at the ceiling but above the ceiling and using that as a guide to when we should end the test. So we would still have a test article to work with. So our initial test was a mixed cell test. Not unsurprisingly, it's essentially a cardboard fire. All the older battery chemistries use a water-based electrolyte. They are essentially non-flammable. So in this case, we let the test run for over an hour and a half. We had a smoldering cardboard fire, got relatively low ceiling temperatures. Fire temperature itself, we never got above 1,000 degrees. We did fill the cockpit with smoke, but got no smoke, not the cockpit, excuse me, the main deck with smoke, but no smoke into the flight deck. And one other thing to keep in mind is this is an empty airplane. This is the only flammables that are in the aircraft, unlike you would see in a more real-life instance. So mixed cells, not really a problem. We repeated the test. Actually, we repeated this with 2 different lithium-ion tests, one with the simulated thermal runaway and one with the adjacent fire. Got very similar results. We let the fire run about an hour. We only consumed about half the cells, so you have a very long-term fire with lithium-ion cells. Ceiling temperatures reached almost 1,500 degrees, which is right around the certification level for aircraft cargo compartment, cargo liner. Battery temps hit about 1,300. We did dramatically decrease the oxygen in that compartment during the fire, which did slow the fire down, but it did not stop the propagation from cell to cell and the release of the flammable electrolyte. We did experience some light smoke in the flight deck near the end of this test, and we also did some significant damage to the aircraft. Even though we didn't penetrate the cargo liner at any point, we had to replace a lot of it prior to the test, prior to running the next test. Can I have the video, please? This is the, I got to skip a slide. Can I go back one? Sorry. Moved on to the metals test. It looked the same to me. This test again ran about 16 minutes before we had to shut it down. In this case, the aircraft was in danger of getting a new sunroof in the ceiling. We only had consumed about half the cells in that 16-minute time frame. Ceiling temps exceeded 1,700 degrees. We're not exactly sure what the battery stack temperature was because our thermocouples peak at 2250. We easily exceeded that. Oxygen starvation with lithium metals had very little effect in slowing down the fire intensity. And probably the most significant, we got smoke on the flight deck less than 4 minutes from the first observable fire. And we were fully obscured within 6 minutes. And again, we did significant damage to the aircraft. And I do have a video of that test, which if I could have that run, please. At 9 minutes from the time we turned the heater on that simulates a thermal runaway, we had the fire break out of the boxes. If you keep an eye on the clock counter, it skips ahead a little bit, but fire buildup was incredibly rapid. So it's actually probably about now you would begin to get smoke warnings in the cockpit, smoke detection. And at this point, you've already got a pretty good fire. So here we're roughly a minute from the time we first saw the initial flame. The smoke is already beginning to build up within the compartment. You would see a more rapid buildup in a compartment, obviously, that is full of cargo. The image on the right is a infrared view because we shortly lose the visual. We're now 2 minutes from the time we saw the first flame. The image on the left is a visual looking forward in the flight deck. We're not even really 3 minutes or so into the test. Now, this aircraft was slightly fire hardened in that we put an extra layer of cargo liner above the fire itself. So a normal aircraft, you might have had penetration earlier. So at this point, the flight deck is fully obscured, and we are extinguishing the fire with copious amounts of water. So just a little rehash. We ran the 2 different ignition sources. We simulated the thermal runaway. We also used an external fire to initiate the battery fire. And except for a little bit differences in timing, we saw very little difference, or no difference at all, in the final effect and the final fire. Looking at the Class E tests, how well did the compartment do in containing these tests? With the mixed cells, it easily contained the fire. Lithium-ion cells, we would call it marginal in that we didn't have any penetrations for an hour, but in reality, if we had gone much beyond that, we would have had some areas where the cargo liner would have failed. The lithium metal, flat out did not contain the fire. We in no way at all did the Class E concept work with lithium metal batteries. Now I have one more video, and I just included this to give you an idea on the explosive properties of the hydrocarbons released when these batteries go into thermal runaway. To set this video up, we're doing some work looking at charging stations for tablets. A lot of airlines are going to tablets for passenger entertainment, and they're using these charging stations where you have multiple tablets and a container all hooked up and charging. In this particular test, we used a galley cart to simulate the charging station, and it only had 5 tablets in there, of which really only one of them got involved in this fire. And I'm going to let it play here. What happens is it's self-ignited, which sometimes happens with an ion cell. We had a pretty good fire going. This was in a 737 test article that we have. We had an explosion that actually put itself out, But as you can see from the smoke coming out, there's still hydrocarbons being released by the burning cells. So not being content to let it go at that, we decided to give it an ignition source, and we got that. Even though I didn't talk about our Class C work today, we did have an event with one of our Class C tests where we had an explosion in the aircraft that resulted in significant damage. And if you want to take a look at that, you can go to our website. And if you search on lithium batteries or look through any of our recent triennial proceedings, any of our systems meetings proceedings, you can find a wealth of information on lithium batteries. Thank you.
Thank you, Harry. Turn it over to John.
Okay, if I could have the presentation up, please. So first of all, thank you for that, Harry. The work that my company's been doing has really been looking at how can we protect lithium batteries and equipment containing lithium batteries at the package level. Very brief background. My company specializes in fire and thermal management. Many of you probably use our products every single day but have no idea you're using them. We do many things ranging from the technology that protects or enables carpet in aircraft to meet low smoke and toxicity as well as flammability requirements, all the way through to cargo liner repair products that maintain the integrity and fire performance of the cargo liner. So what does that all mean with regards to lithium batteries? So some years ago, there was a rule called HM224B, which really covered the shipment of oxygen generators and oxygen cylinders. And there were two key aspects to this rule with regards to flammability. The first thing was that oxygen cylinders and generators needed to be packaged in boxes and containers that would prevent flame from exiting or entering the package and causing either the oxygen generator to ignite or the oxygen cylinder to vent and obviously, add oxygen to the fire. The second aspect of that rule was also in the event of a halon-damped cargo fire, the inside of the packaging needed to stay below either the self-venting temperature, which was 200 degrees for an oxygen cylinder, or in the case of an oxygen generator, not allow sufficient temperature to cause the oxygen generator to ignite and therefore, again, add to the fire. In response to this rule, Akro developed a range of fire and thermal pack technologies, and together with Americase, we developed a complete range of HM224B packaging solutions. So in then looking at, beg your pardon. So then looking at future sort of like hazmat challenges, obviously lithium batteries then became, to the forefront of a real challenge. So we decided to look at how could we use our HM224B experience and technology developments, and then use that to mitigate the threat of lithium batteries at the package level. The existing concepts that are out there are very much based on our work we did with the HM224B work, which includes rigid metal containers containing the fire pack technology, together with a simple overpack containers which are designed to just stop a small-scale fire on the inside of the box. The real challenge in creating a packaging method is really the incredibly broad spectrum that covers lithium battery shipments. The oxygen generators and oxygen cylinders were very, very defined shipments, but as we've already discussed, the sheer quantity of batteries being shipped and equipment containing batteries make a challenge in coming up with a packaging methodology. So the concept that we've developed is it essentially is a free-flowing, loose-fill packing nut that, following exposure to significant heat and fire, forms a contiguous, rigid, protective barrier. The key properties to these packing nuts are that they're heat-absorbing, they're heat-resisting, they have a very high temperature stability, they'll gap-fill, but more importantly, they're versatile. And what we mean by versatility is that you can use common packaging that is in regular industry use, i.e. a standard hazmat cardboard box. For the testing, we looked at in the absence of any clear definition of what testing requirements we would need to do, we drew upon sort of work the FAA had done as well as HM224B and really settled on 3 key areas. One, we needed to protect the batteries or the equipment containing batteries from an external fire. We needed to protect the batteries from heat, either the cargo or the damped cargo fire scenario, and then also containment. And that is, in the event of a thermal runaway incident, we needed to contain that in the package and prevent that spreading to adjacent packaging. In terms of the sort of the threat level or the threat model we used, we chose to use the lithium metal batteries, and in particular the CL123 cells. These are highly energetic and they render a much more conservative testing when compared to, say, the lithium-ion secondary rechargeable cells. But for our testing, we really wanted to test the packaging and really understand how well we could contain the threat. Just as a reference point, a typical CL123 is approximately the same power capacity as a fully charged smartphone. So this picture gives you a good indication of what we're really talking about here. First of all, you have OEM packaging, in this case containing batteries, but that could be containing cell phones or a laptop or a tablet, etc. That is then placed inside a standard cardboard box on a layer of the loose-filled packing peanuts. And then that in turn, the space is then filled with the peanuts, and then the box is closed and simply taped shut using, again, standard hazmat practices. So the first test that we really looked at was the direct flame impingement. And we wanted to use an industry-recognized performance requirement. So in this instance, we used the FAR 25855, which is the cargo liner test. And essentially, this is approximately 7.5 BTU flame with a minimum flame temperature of 1600 degrees Fahrenheit for a 5-minute duration. And for us, we're looking at ensuring that during that 5-minute event, that the batteries aren't affected by the fire. And affected means that, first of all, they don't go into runaway, and they're not actually adversely affected. So we need to keep the temperature and the flames away from the batteries. If we have the video, please. So here you see the burner being swung onto the box. As you would imagine, very quickly the cardboard disintegrates under the fire threat. And as you see here, the actual packaging is actually swelling up and fusing together and providing that continuous or contiguous barrier that I mentioned earlier. The next test we looked at was the suppressed cargo fire, which is a thermal resistance test. And in essence, what we're trying to do here is look at a damped cargo fire in a maximum sort of diversion time for that type of event. And so that was from the HM224B rule, was really a 400 degree Fahrenheit environment for 3 hours. And in that time, we wanted to make sure that the packaged batteries or equipment wouldn't reach a temperature which would cause the batteries within that equipment or the batteries themselves to go into thermal runaway and then start to contribute to the fire. So just as a point of reference, the work we have been doing indicates that lithium metal batteries can go into runaway as low as 350 degrees Fahrenheit, lithium ion 450 degrees Fahrenheit, and then lithium polymer 330. Here you see on the pictures the box after the fire or after the oven test, and as you open the box, you can see the packaging is fused together, and this gives a very good picture of what happens, after prolonged exposure to heat. And as you dig into the packaging, you can then return get to the actual piece of equipment you're shipping, and it's unaffected by the temperature. The graph, although difficult to see on the screen, the top line shows the ambient temperature of 400 degrees Fahrenheit in the oven. And then the lines going down the graph show different temperatures through the packaging, with the lowest one, which indicates that the packaging stayed just below 200 degrees. So well below the sort of temperatures we would expect to see any of the lithium technologies going into runaway. The next challenge is the thermal runaway. And if I could have the video. What I wanted to show here was just 8 cells going into thermal runaway. We're initiating it using a cartridge heater, which you can see on the right. As soon as the cells go into runaway, we disconnect the cartridge heater. But I think this gives a very vivid indication of what happens when these cells go into runaway. And we're talking about cells that are little more than an inch in height, so a very small, compact area, but an incredible energy density and a resulting fire. So what you see is, as a cell goes into runaway, you first of all get venting of the cell, which results in sparks and flames. And then a very rapid temperature rise, which then spreads to adjacent cells in very much in a cascading effect. All of the videos I'm showing you have no sound because grown men screaming can obviously be upsetting. So, as I mentioned, testing in the thermal runaway, we're looking at using a cartridge heater that's inserted in the group, and typically in all of our tests, we're fully consuming all of the cells in a cascading runaway. And the cascade, or the runaway, really runs or covers three significant areas. The first is the volatile components vent from the cell, and that results in a smoke or mist which will ignite. The second stage is the internal cell components mix to produce a violent exotherm, and we regularly see cell temperatures up to 2,000 degrees Fahrenheit in our testing. And then the third stage is then that propagates to adjacent cells, resulting in an increased conflagration. So, as we've been developing this product, we wanted to look at what other packaging or recognized packaging methods. And one thing that keeps coming up to, at the forefront in hazmat packaging, for lots of product, but also cells, is the use of vermiculite. Primarily for road transport and ground transport type applications, but it is a common method of transporting lithium batteries and lithium battery containing equipment. So we really wanted to see how vermiculite would cope with, say, 100 cells of the CL123. If we have the video, please. Again, the vermiculite is packed in a standard hazmat packaging box. And what you'll see as this video progresses is vermiculite is being forced out of the box as the pressure rises up inside that box. And very quickly, the cells in runaway overcome and will ignite and then actually exit the vermiculite, and you have a pretty uncontrolled fire at that point. And I think vermiculite is chosen because under available regulations, it's determined non-flammable. So in our testing, we've tested up to 300 cells, and we've really stopped at that because we feel that 100 cells represents a viable, practical packaging method for the types of applications we're looking at, which is the smaller boxes of cell phones or laptops or equipment, damaged or defective equipment, etc. And here you can see, typically after, both before a test and then after the test. The post-test, the box is all intact. As you open the package, the packing peanuts are fused together, and then as you dig into the cell, you get to the remains of the cells, which have all been gone into thermal runaway and have fused together. And if I could have the final video, sorry. And this is that test. And as you can see, at this point, all of the batteries are in runaway. We're getting temperatures just below 2,000 degrees Fahrenheit in the center of the packaging. But the cardboard box is containing that event. And so, in terms of what's going on in there, this graph gives a very good indication. Unfortunately, you can't see the clarity on the screen, but the first blue line you see there is actually is a cartridge heater. And as the cartridge heater heats up, the adjacent cell, which has a thermal couple to it, also heats up. And when that adjacent cell goes into runaway, then we disconnect the cartridge heater. And you see this rapid rise as that cell goes into runaway, and then all of the adjacent cells going into runaway. Interestingly, at the very bottom of the graph, you'll see the line there, and that's the external temperature of the box itself. And we're typically getting an external temperatures of around 200 degrees, which is well below the ignition point of cardboard, which is around 400 to 500 degrees. So, in summary of the available options, we have packaging out there available for shipping lithium batteries now, and that can range from the aluminum super box, which is a thermally insulated battery shipper, and is very similar to the oxygen cylinder container developed for HM224B. A simple fireboard box, which is designed only to contain a battery fire or limited numbers of batteries, and then all the way through to the loose fill or the packing nut concept that I've talked about just now. So in conclusion, the loose fill concept provides a practical and economical and, more importantly, flexible method of enhancing the safety of shipping lithium battery and equipment, lithium battery containing equipment. Broader logistics will likely dictate the type of packaging, i.e. reusable versus single use. But these packaging methodologies supported by testing provide a practical and effective option for the shipment of lithium batteries. And threat mitigation at the package level is an important element to a multifaceted approach to safety in shipment. Thank you.
Thank you. Today I want to talk with you about the work that we're doing at UPS to improve freighter fire protection during any type of smoke, fire, and fume event. Before I really begin the presentation, I want to talk about what our safety task force is. I'm a member of the UPS IPA Safety Task Force, and what that is, it's 3 members of management and 3 members of our pilot association that came together after September of 2010, after our tragic Flight 6 accident, to work at ways to make certain that that type of event wasn't going to happen again, to the best of our ability. So we started out by trying to see what was available in the aviation industry, and really we didn't find many good solutions. We talked to industry consultants. We asked questions like, how do they put out a fire in a submarine? How do you deal with a smoke event in a closed space? How would they deal with something like that on the space station? How are batteries made? Where are they made? All the types of questions you'd want to ask if you're going to solve a problem. There were some existing aviation products that worked, like full-face oxygen masks and the EVAS, Emergency Vision Assurance System, but there weren't a lot of other solutions that could really help contain a fire. Some of the solutions we found outside of aviation came from the aerospace industry. We have some elements that we brought in from the US space program and even the Russian space program to help make things safer. And finally, we talked to the real experts in firefighting, and that's the firefighting community, both at the FAA Technical Center, and we even attended a firefighting convention and saw the fire trucks, but found some interesting solutions there that didn't exist in aviation, but did exist in their industry. The type of products we're flying today are different than what we've flown before. Our business air model has changed, and it really has to do with the cost of energy in a battery. In 1991, a battery was $3.17 a watt hour. Now it's down to 12 cents a watt hour. You may have read the article this weekend about the research being done at Stanford and nanotechnology and lithium batteries. They expect to make a battery now that's going to have 3 times as much power at 1/4 the cost. So what we're going to see is an escalation in the shipment of batteries because the battery energy is getting cheaper, and that's kind of what it's all about. Although the battery stopped working in this remote.
It's the revenge.
Yes, it is. Next slide, please. Wrong
In
presentation,
conclusion.
right? I'm pretty sure this is a Portable Battery Recharging Association getting back at us, but thanks. Here's a slide, and it really just echoes what you've heard earlier, that there's getting to be more and more batteries manufactured, more and more being shipped. This is a study that was commissioned by the FAA by R.W. Cherry and Associates, and each one of the red dots you see represents an aircraft accident that was attributed to a fire. And the dot in 2010, that is UPS Flight 6. What you don't see is just slightly to the right of that would be another red dot, and that would be Asiana Flight 991, 747 that has an accident attributed to batteries. But the reason you don't see that is because this study dealt with U.S. domestic freighters, and probably the most shocking statistic out of that whole study was that 6 accidents are likely to occur between now and 2021 of domestic freighters. Now that's if no mitigation strategies are incorporated. This same research that the FAA had done, it's an Excel spreadsheet. It allows you to put in mitigation strategies and see what you can do to reduce the risk. So now you understand that there's more batteries being shipped and the risk is going up. So let's talk about how we can protect us and protect the flight deck. And the pilots are really the last line of defense of that. We found there were 2 things we could do right away that would improve safety. And the first is taking a look at the oxygen masks that we carry on board our aircraft. Our aircraft primarily had 2-piece, the mask goggle combination, which takes in excess of 20 seconds to put on, and it takes 2 hands. We have since converted all our aircraft into a full-face oxygen mask, which takes 1 hand to put on, and it goes on in less than 5 seconds. In addition, it's better for eyeglass wearers. It does a better job at preventing toxicity from entering to the pilot. So it's just a marked improvement. We also took our supernumerary aircraft, area of the aircraft, and where we had Dixie cups for the passengers and for the jump seat riders, we replaced that with oronasal pressure breathing masks to better protect the occupants on our flights. The other improvement is EVAS system, the Emergency Vision Assurance System. And what that allows you to do is once it's inflated, it allows you to see both the flight instruments and outside the cockpit window in a densely filled smoke environment. I put this picture up to show you what it looks like. This is a 757 simulator, and there's actually 2 units, one for the captain, one for the first officer. They deploy in approximately a minute. We did an independent study of this technology. We took a simulator, we introduced smoke into it, we had some experienced pilots flying it, and in a heavily smoke-filled environment, like UPS Flight 6 was, they lost control of the aircraft in about 2 minutes. And then we did the same test, reintroduced it, but allowed them to use the vision assurance system, and they were able to safely land the airplane in both instrument approach and visual. So it's that kind of technology. It represents the last line of defense, but it truly works, and it's an improvement. We also looked at how we train. There's a standard called CAP 676, and that has to do with human factors design and checklists, and it was put together by NASA, the FAA, and EASA. And so we've tried to introduce some of their human factors concepts into our checklist design. Things as simple as numbering the steps that need to be done in a checklist. They find that if you're interrupted in your checklist, it's much easier to know where to go when you have those steps numbered. Or maybe expanding on what the condition of the problem is so you're in the proper checklist, and enunciating confirmation steps. All those kind of human factors, very simple type of things to do to make it better. Our airline, like I think many airlines, also used to train emergency equipment as individual modules. You might learn about a life vest and then a fire extinguisher and perhaps your oxygen mask or what kind of firefighting rescue equipment was available. But we talked with education experts, and we found that there's a thing called sequence-based instruction, and the order you learn something in really makes a difference if you're going to remember how to do it when you're called upon to do it in an emergency. And so what we've done is we've reordered some of the ways that we're training. We're training those same modules that we had trained before, but we're training them in a sequence. So when you're called upon in an emergency and you have to recall from A to Z what to do, and in this example, an onboard fire and putting your mask on and deploying your EVAS system, and can you fight the fire, and what kind of ARF equipment would be available on the ground. We're trying to train now in a sequence to better educate the pilots. But finally, we come to what I think is probably most relevant for the audience today, and that's protecting the aircraft. And what we found is that some new materials and designs are really making a difference. At UPS, we have incorporated fire containment covers over palletized freight now. And these covers are used from the origin to destination. So if something's leaving Hong Kong but it's going to Miami, it's covered the whole way, or wherever in the world it is going. And we cover two types of things. We cover anything that we know is an energy shipment or battery type device, and we also cover things that we don't know what they are. When a pallet would come to us from a shipper and we're not sure if it has electronics in it or not, we err on the side of safety, and we cover that shipment as well. Pallets of flowers, we don't cover, but if we don't know what it is, we're covering it. We were putting a cargo net over it anyhow, and we've engineered a way to utilize these covers. It takes no longer to put them on. Yet these covers, they've demonstrated a 1,500 degree protection up to 4 hours, and that's been a goal that we've established. 100% of our flights could be on the ground somewhere in 4 hours. We've also done a lot of work in engineering unit load devices. And when we first started this, we found that our ULDs would fail after about 8 minutes if there was a fire on board, or maybe as long as 20 minutes. And so we established that goal of 4 hours, and using a new material called macrolite, we've been able to consistently have a 4-hour fire containment of a Class A fire. And that material is actually lighter than aluminum, stronger than aluminum. It has some good ballistic properties in case batteries were to be firing around, but the most important thing is the safety margin it provides, that 4 hours of containment. Right now we have more than 2,000 of these containers in service, and we just placed an order for another 1,400. So we're really happy with what's going on in that regard. What we're working on now and next is that same ULD, but putting a suppression system in it. And right now we've applied for an STC. And the reason we like this system is because every position in the aircraft would be covered. Not only that, it offers multimodal protection, meaning that these containers can roll off an aircraft, roll onto a semi-truck, roll into a sort center, and for that entire transportation sequence, our employees are protected, the facilities are protected, it just offers that all-around protection. So certification testing is underway right now, and I'll tell you, it's a tough project, and we've done a lot of tests, and this isn't an easy solution. It's taken a lot of engineering effort to get there, and we're not there yet. We're very close, and still working on the certification. What I want to do now is show you a very short video. It was actually made in October of 2012, but I think it really illustrates the points of what it is we're trying to accomplish at UPS.
The FAA and UPS IPA Joint Safety Task Force are getting ready to start a fire, but first they need something to burn. So they're putting together a container load of test packages, books, NTSB, who says UPS's container and suppression solution is very promising.
The goals of the NTSB for cargo fire safety are to be able to detect a fire very early and to be able to suppress it before it grows and becomes a threat. And these tests look like they are achieving that objective.
The fire goes out quickly, the smoke clears, and after the 4-hour demonstration, all that's still burning are some embers in the ignition box.
We are able to contain the fire with just containment, but adding suppression to it gives the extra benefit of extinguishing the fire within the container.
The fire suppressant is so effective that not only is the fire out, but more than 95% of the packages in the container are undamaged, including a bulk shipment of lithium batteries.
Right now, we just demonstrated that this container can suppress a fire for over 4 hours, and the fire is basically out. And that means the difference between life and death. It allows our crew members the opportunity to get that airplane on the ground safely, save not only the crew, but the airplane and our customers' packages.
UPS is still in the research and development phase, and there's significant work to be done. The suppression system may be modified, and a new solid door has to be designed to replace the fabric roll-up doors used on many types of containers. Once development is complete, any container modifications also must be tested in regular operations and certified by the FAA. But work is continuing, and the progress so far has been remarkable.
To be looking at a ULD that can contain a fire for 4 hours was unthinkable a year ago. And we continue to see that here at the Tech Center every test we have. What this group has been involved in is something that's going to change the industry.
So I want to leave you with some final thoughts. Enhancing the aviation safety is possible, and we can do this. Some of these new technologies are showing great promise. We need to work together, and when I say we, I don't mean just the pilot associations and the airlines. I think the regulators have a hand in this. I think the battery manufacturers have a hand in this. I think some of the work being done in packaging is important. I think it's a multi-layered solution to reach the objectives that it is that we're trying to reach. And probably the most important final thought is that these cargo fires can become survivable events. Today, if you have a cargo fire, on average, you have 18 minutes before there's a catastrophic end to that event. And when we're able to continue to fly for 4 hours and land safely and go home to our families, I think that means everything. So collectively, we need to work together and make these cargo fires survivable events. Thank you.
As they're pulling up my presentation, I just want to say thanks to Mark and the ALPA leadership to provide me the opportunity to sit on the panel and give you a cargo pilot's perspective. As depicted, when my slides come up, I'll be concentrating my discussion on fire suppression. Assuming most are familiar with the Swiss cheese model, I'd like the audience to think about fire suppression as just one of the systems in a layer of safety technology systems for that end. Currently where I work at FedEx, much has been done and more is planned for fiscal year 15. As you can see from nose to tail, a lot of safety improvements, and these are just the ones focused on fire suppression and cargo fire management. EVAS will be deployed this year at FedEx. We've had full face oxygen masks, and we've enjoyed them for over 10 years at this point. Fire curtain and rigid cargo barriers have long been deployed in the cabin area. Things that are new and under development are fire containment covers, as well as thermal bags for the belly freight. The main deck fire suppression system in the MD-11 and 777 is what I'll spend some time looking at in later slides. It's worth noting that these cargo fire management technologies sync up with CAST, Joint Safety Implementation Team recommendations found in Safety Enhancement 127. That's dated back in late 2008. At FedEx, there's been modifications made to several container devices. Containers with an open side have been modified with a fireproof curtain and clamshell locks to improve suppressant retention within the container. There have been modifications made to the fire containment covers that are put over DG freight tied down to pallets for transport, much like you saw with UPS. And the meat of my discussion will be the implementation of our fire suppression system on FedEx MD-11s and 777s. But before I start to describe that system to you, it's better that you might visualize another system you might already be familiar with, because it's mechanized very similarly to our fire suppression system. We've come to think of a camera and microphone hovering just above and behind the quarterback and running backs in college and professional football games as the norm now. That system is known as Skycam or cable cam, and depending on what network you're watching. It's an automatic and autonomous system that goes wherever the football goes, up and down the field, left and right to each sideline, using a system of cables strung over top of the field. Now transition to the MD-11 football field or main cargo deck, as depicted in the fire suppression system display. The front of the airplane's main cargo deck is at position 1 to the right of your screen, and the back position is 14 where the tail tapers. The green squares represent positions where each container is located. 2L representing the second left position and 3R representing the third right position. Mechanized just like Skycam, moving a camera up and down the field where the ball is, this automatic and autonomous system moves a punctuator actuator that you'll see in a few slides up and down the fuselage where the heat is and executes its function, delivering fire suppression foam to a smoldering container. That's the inside of an MD-11. As you can see, there's a skeleton framework on the ceiling that allows that punctuator actuator to move up and down, left and right over the top of the containers in the main cargo deck. Next slide, please. There we go. So over each container position are thermal sensors to detect container temperature above a certain level or a rapid rise in a container's temperature. The fire suppressing agents are a combination of argon gas under pressure used to push the fire suppressing foam or surfactant that moves through the skeletal tubing that you viewed 2 slides ago. Argon was chosen because it's an inert gas and one of the least reactive elements out there to choose from. Similar to Skycam, moving to where the ball is, the penetrator actuator moves to where the heat is. Then, when overhead the hot container, it thrusts a sharp penetrator into the container and delivers the foam to suppress the fire or whatever is causing the thermal increase. The upside of the system, it's automatic and autonomous, allowing a notification to come to the cockpit, allowing me and my first officer to land at the nearest suitable airport. The downside, it's good for one shot. If another container has a thermal event after initial discharge, it's not there to help you. This system may not fully extinguish a lithium battery thermal runaway, but it can suppress it in a way that buys time and allows us that time to get on the deck. So this is a good safety technology layer. It's not a silver bullet for all fires or all thermal events. We need to continue developing other technologies for that layered approach. So this is the here and now risk, as our other panelists have described. The going in position for me is a thermal runaway of a lithium battery is a significant risk. And when you add them together, it's a greater risk by a lot. So moving to future safety technology, research and development at FedEx is important. The CR123s you see on the left get packaged in 4 trays that stack on top of each other in the box you see on the right. There's about 300 batteries in each tray. FedEx is developing a performance-based packaging with a proprietary liquid gel coolant that has a very unique heat transfer capability. It actually should be labeled a liquid coolant that turns into a gel as it absorbs heat. It's reusable. The shell surrounding the liquid coolant ruptures at a predetermined temperature, and then because of the heat, the liquid coolant coagulates into that gel around the runaway battery, reducing the risk posed by a ripple effect to adjacent batteries from heating up and running away. Some practical development on this technology as it matures. It requires a coated tray to keep the liquid gel or coolant from absorbing into the cardboard once released from its plastic shell. So if you remember the picture of the tray of 300 batteries, this white coated tray would fit inside that cardboard tray. The liquid gel coolant pack would sit on top of the batteries, and at that predetermined temp, the plastic ruptures, the liquid oozes out and coagulates around the bad cell. That reduces risk for that tray of batteries. If they're stacked on top of each other, then it's another variable to add to that risk equation. But it's a very good potential layer to add to our safety technologies. Another safety technologies we're looking at under research and development is a performance-based mask. Now, unfortunately, it's not this guy's mask or his suit, and it's not that guy's mask. It's an off-the-shelf product that we've been using for all of 10 years at FedEx, a full-face oxygen mask. Except this mask has an eyepiece similar to a Google Glass, if any of you guys wear that out in the audience, and it's integrated into the mask. It shows the integrated HUD display and serves not only as the primary attitude instrument, but overlays an infrared picture into the HUD field of view so that you see that regardless of what's going on outside the mask and inside your flight deck. So another technology solution with off-the-shelf products, another layer of safety. From a pilot's perspective, no doubt, fire is a severe safety risk on aircraft. Not all fires or heat sources have the same properties, which means no one solution is a golden BB or silver bullet. Technology solutions need to be layered. Right now, the operators are the ones leading the way. Time is that critical element, and layered solutions give us that time. Time gives you options, and as my dad always told me, options are good, especially when they're yours. So a common level of risk needs to be understood, and our teammates at the FAA are helping all the stakeholders through their testing understand what that common risk is. And with that, we need to ramp up and accelerate our battery testing to further capture data for the here and now and the increase of battery shipments that are coming in the future. All this said, we need to set conditions and execute control over this dangerous good. We need to know specifically that it's on our aircraft, how much there is, how it's packaged, and where and how it's loaded. Is it on the main deck? Is it in the belly? Is it in that pallet bag, or a DG can, or another ULD? And no matter how the regulations follow this line of thinking, the intent should not allow for a single box of a certain number of lithium batteries to be under the minimum regulation threshold requirement for DG identification, then an overpack by adding 300 more boxes to that shipment on that airplane. So, moving from tactical to practical on that, imagine my MD-11 flying from Memphis to Milwaukee, and my first officer and I are 50 miles south of Chicago, and we get a cargo fire indication on the main deck. First, we both put our oxygen masks on, and then immediately head for the nearest suitable airport with a 500,000-pound airplane with 50,000 pounds of fuel and 100,000 pounds of freight to make an emergency landing. But a cargo fire is a different type of emergency. See, our airplanes are designed to lose an engine, and we practice that, and we land consistently with a lost engine. This is different. We don't know the outcome to a certainty or a level of certainty like we do with an engine failure. It's a level of emergency like few others, and the nature of this emergency as I go to that nearest suitable airport puts everyone beneath my flight path at risk. So, with that, I'd like to have a happy ending with a cargo fire, but in the risk equation, we need to incorporate the risk to the American public below our national airspace. So the fatality cost basis metric used by the OMB only accounts for people on the aircraft. This is a poor metric for safety performance. It's just, to me, it's obvious. A cost basis for human life present on the aircraft determines the risk for only one part of that equation. A metric that accounts for the risk for the people below my flight path is a better equation. As I close, I have a challenge for our safety stakeholders in our aviation community. When talking about passenger and cargo operations, I want our industry to move out of phrasing safety in an either-or paradigm and move to a both-and. Requirements for safety should be not based on either passenger or cargo, but safety regulations should be one level, consistent for both passenger and cargo. Thanks very much for your time. Appreciate you listening, and thanks to our panelists. 20 minutes for questions.
I'd like to thank everyone as well. We're close to back on time. I would like to afford the opportunity for a few questions from the audience, especially considering all the work the panelists have done in presenting this information. I think as a summary, you can tell that there is certainly a risk out there, and that risk is going to increase in the coming years with the number of lithium batteries that are going to be shipped. There are promising solutions from a packaging level all the way up to a container level. We have several different packaging solutions we've heard about, container-based suppression and aircraft-based suppression. But of course, none of this is required today, and there are only very few airlines that are looking at doing this. The vast majority of operations out there have nothing approaching this level of protection. And also from a regulatory standpoint, I want to remind everyone there is nothing in the regulations that prevents filling an entire freighter aircraft with only lithium metal batteries. And there's nothing in the regulations today that prevents filling an entire passenger aircraft, the cargo compartments in the United States or throughout the world, full of lithium-ion batteries. Both of these situations are allowed today, and both will continue to be allowed in the future. So with that, I'd like to open it up to a few questions, if anyone from the audience has anything. Thank you.
I'm John David, NAV Canada. I found your presentations very interesting, and you seem to be embarking on lots of research for suppression and for survival. And I looked at those containers that you're developing and how you're building them for protection. And obviously the lithium-ion battery is a serious problem for us in this industry, and it's heat related. So has there been any consideration for the development of these type of containers that are refrigerated units that have very, very tight temperature sensors on it so that it's kept at a low temperature to mitigate some of the heat cook-off initially, but also to reduce the rapid escalation of heat? And then you can monitor it in the cockpit with the type of system, Rick, that you're talking about looking at, in an isolated area. And within these containers, you've already thought of the self-suppression. And the nice thing about the container and containing that is it's sort of like when you take a guy for a ride in the back seat of a fighter and he honks, it's kind of nice if he had a honk bag because you don't have as much to clean up after. So anyway, I just wondering what you've looked at for refrigerated units. I mean, we do it for transferred frozen foods all the time. We don't let them perish, and we monitor and maintain that. Is that an option?
Take a stand with that. We do have refrigerated units that we use for medical supplies and that type of thing, but the suppression system that we're installing in our aircraft, that has cooling properties. That will lower the temperature 700 degrees once that agent is dispersed. What we found in our testing is that seems to be sufficient. In fact, when we talk about that fire being put out for 4 hours, that fire is put out for 24 hours.
Yeah, I understand that. I'm all in favor of putting out fires, but I'm trying to say getting rid of the problem before it gets to the fire by having these sensing things. So if I'm flying from A to B and I've got a monitoring system that says this temperature is going from -30 or whatever the predetermined temperature is, and it's going up to -20, going up to minus, like my radiator in my car, I got a signal going on saying, we got a problem, and we've isolated it to that container. We got to get this thing on the ground at the nearest airport and ASAP before it cooks off. And that's what I'm talking about, getting even way ahead of this. I mean, once you got a fire and you have to put on your masks and all of that, that's another issue. But we have the capability, I think, today to get it before it even cooks off. That's the point I'm trying to make.
That's a good point.
Thank you.
Good morning, gentlemen.
Good morning.
Good morning, okay, thank you. Patrick Mazzola with United. My issue is I'm flying over the ocean with about 250 people in the back. From this discussion, I'm certainly glad we don't carry the batteries in our cargo holds anymore. However,
we do.
I personally...
Absolutely we do.
We do? We still, okay, I thought that was, I thought our company stopped doing that.
No.
But, so I personally have 4, and I'm sure everybody in the back of the airplane's got at least 2. Mr. Webster, thank you for I've got the website down there to pass out to my company as far as putting out a 1-unit fire. The only direction I've got is to dump water on it. You can imagine the back of the airplane with a bunch of passengers and flight attendants running around screaming with something burning with what we've seen on these videos. Is there any other guidance for me on dealing with that over the ocean with no place to go, at least an hour out? And how do I deal with that fire in the back?
You're talking about like a laptop fire or a cell phone or something along those lines?
Everybody's back there charging up their units and...
Go ahead.
I say, fortunately, a single unit like that does not present a huge risk to the actual aircraft.
Okay.
At this time, we recommend that you initially attack it with one of your Halon 1211 bottles to put out the surface fire and to also make sure it doesn't spread to any other flammables. And at this point, pouring water on top is extremely effective. What you're trying to do here is stop any additional cells within the unit from also going into thermal runaway. Remember, these are discrete fires. Each cell is a discrete, separate fire within the package. So they don't all go off at once. If you get water on it right away, you can cool the product down so that you don't spread to the adjacent cells, and you essentially have ended the threat.
And just to add to that, some of the work we've done within ALPA, we've had worked with ICAO to put the response guidance in the ICAO emergency response booklet. IATA's put out information. I've gone to the management of United and other airlines. I've presented at Star Alliance Safety Vice Presidents meetings. We've initiated training for flight attendants throughout the industry. We've put training for pilots at different carriers, including United. We've got information currently in the CQB segment that's out there right now for United pilots. We've put safety bulletins out from ALPA, from ALPA. We're continually trying to get out the word because if you have the proper procedures and the proper training, it'll be a survivable, while exciting event. But the challenge is continually getting that information to the flight crew so that they know what to do.
And does anybody know for the typical unit that a passenger I'm carrying, would it be metal ion or?
Generally ion for the
Ion,
rechargeable
okay.
batteries. So cell phones, laptops, those things are normally ion, but you will have metal batteries in the cabin for cameras, flashlights, things along those lines.
Okay, thank you.
Time for 1 or 2 more.
Hey, Mark, Scott Reeves, FedEx, thanks for putting together a great panel. But the question I have for Mr. Webster, you mentioned at the same time you're doing the Class E studies, you were looking at Class C compartments. And from where we are right now, tomorrow night, how are we going to ship stuff perspective, we're trying to determine whether there's risk mitigation by putting lithium metal, lithium ion batteries in the Class C compartment versus the Class E, because there is some suppression. So what were the results of your test of the Class C, and is that any risk mitigation at all by putting the cells there?
The short answer is yes. The Halon 1301 was very effective at suppressing lithium ion fires. Keeping in mind that it does not stop the progression of thermal runaway, so you still have that huge accumulation of flammable hydrocarbons. But as long as the 1301 concentration remains high enough, then you have protection against both explosion and fire. The The case is a little murkier for lithium metal in that you still have a pretty decent fire, but the halon does protect a little bit against that by reducing the electrolyte portion of that fire. It's not a very good answer for metals, but it is a reasonable answer for ions.
And did you guys look at the risk difference between upper deck fire burning through the crown of the aircraft versus a Class C fire burning through the floor with control cables and lines and what have you?
Not that specifically, no. But we did find that the Class C compartment handled ion fires very well. Metals, not nearly as well. As far as where you're going to do damage to the aircraft, that wasn't part of our test protocol for that one.
All right, thank you, I appreciate it.
I think we have maybe time for one last question from the audience. Bob?
Bob Siskram, United. And Mark, you already know this because you're the one that I send the emails to previously, but we have a number of pilots already that if they had seen the videos that you showed us today would be done carrying lithium batteries ever. The chances of them carrying them on the airplanes are pretty low, and they're only doing it because we, ALPA, are telling them, look, this is as safe as we can make it right now. I don't think that in this forum, in this room, you're going to find anyone who doesn't support every single thing that you guys are doing. However, if you filled these seats with airline executives, every one of them would be saying, we just can't do that to anything you're doing because it costs money. And the reality is their life is based on the risk of money, and ours is completely different. So you've got an audience here that is very happy to see you and is very somewhat, well, not necessarily very, but somewhat frustrated that we aren't further along in this than where we should be. Cargo aircraft not on the same rules as us is insane. It's stupid and ridiculous, but that's all about money too. So I asked Mr. Webster, sorry to put you on the spot, but the FAA is the only driver here for these things other than us screaming, hey, we need help, we need help, we need help. The company's saying, we're not going to do it because it costs money. And so the decider, if you will, is the FAA. And so what I would like to see as the safety guy from United Airlines is the FAA take a humongous baseball bat to the heads of the administrators and say, what are you doing? This is a no-brainer. You have to do these things. Heck, we have to fight tooth and nail just to get full-face oxygen masks at United. And it's unconscionable that we're carrying these and the cargo numbers are going to go through the roof. Every day there's going to be more, and we're not doing anything about it except for experimenting and saying, hey, there's promising things on the horizon, but it's not mandated. So is there something coming from the FAA that's going to go to A4A and say, sorry, but you're going to have to spend a couple bucks to save a few billion?
Unfortunately, the FAA is currently has its hands tied in our latest reauthorization in that we can't pass any rules that are more stringent than what is currently listed by ICAO, which is why we're working very closely with ICAO, again, convincing them that there is a real problem and looking to get more stringent rules passed on the ICAO platform that we would then adopt here in the U.S. I wish I had a better answer.
And adding on to that, there has been significant progress at ICAO. As you know, I'm also the ALPA Dangerous Goods Chairman, and for the first time in February of this year, we had a multidisciplinary meeting hosted by the FAA Tech Center in Atlantic City, where we didn't limit it to the dangerous goods world, but we had aircraft design and operations personnel from throughout the industry. And for the first time, we had Boeing and Airbus very heavily involved in the meeting. And yesterday morning, we got notice of the second multidisciplinary meeting, which will be hosted in Cologne by IASA in September, and that'll be followed on by the next Dangerous Goods Panel meeting in October. And the remit for the next biennium at ICAO is to focus on freighter aircraft and also lithium-ion batteries on passenger aircraft. And so the trend is very slow, but it is accelerating and increasing, and we move beyond the dangerous goods world. We had very good support from the aircraft manufacturers and certainly others. Mitch Fox is in the room from ICAO, very supported from the other parts of ICAO besides the dangerous goods panel. So I think we're moving in the right direction, just very slowly.
All right, thank you.
Chuck. Thank you.